Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
First and foremost, I want to talk about the methodologies of communicating between MCAD and the ECAD worlds. And then secondly, I'll talk about the most common file types that are related to this. Afterwards, I'm going to turn the floor over to Roger Castro. Roger is a super user of Desktop EDA, and he's going to demonstrate a couple of things. He also has a tremendous amount of experience in this particular industry, and what I mean by that, both the ECAD world and the MCAD world. So he's kind of grown up with it, and he's really, I consider to be an expert in this whole ability to go between these two worlds. And then the Q&A will be with Brian Watson, who is the founder and owner of Desktop EDA. All right, let me get on to it over here. Before we talk about things like STEP and IDX and IDF, we really kind of need to understand the methods that they're trying to use in order to talk between the two different worlds. And if you really think about it for a moment, in the ECAD world, there are things that are very specific to the electrical engineers. And in the MCAD world, there are things that are very specific to the mechanical engineers. And these two domains would not exist separately if they didn't have their own needs. Right? It would just be one big tool. We would all work in this one tool. We'd all be happy campers. But the fact of the matter is, we all have our different tools because they address different issues within the domains that we work in. So the first, and then there's a format. There's usually some way you want to try to communicate between these two domains. And so that's why you start seeing all these different formats show up. So for the first example, you see what I have up here called the universal format, and that is the IGES format is one of the oldest ones out there. And this is a great example of a universal format because the advantage of it is that everybody had to adhere to it. That's the whole reason that the U.S. Air Force actually created IGES back in the 1970s. It's still used to this very day in mil, aero, and auto, and some of the other large industries that have been around for a long time because everybody has to adhere to the standard. And it's great because everybody can talk to each other in that regards. And keep in mind, too, back in the 60s and the 70s, well into the 80s, even a small part of the 90s, too, everybody not only had their own software, they also had their own proprietary systems. Right? They were all working on different computers that were specific to, maybe IBM, Unisys, Burroughs, Univac, whatever they were. These were the, everybody had their own system. So the Air Force said, look, you all have to adhere to the specifications so that you can talk with each other. And that's why they came up with this universal format. Of course, the disadvantage is that, again, this is primarily created for the mechanical guys, but the electrical guys really couldn't pass information to and from to the mechanical guys and vice versa. Okay? And so that's kind of an example of a universal format. Then you have what I'll call the middle ground format, and the IDF is a really great example of the IDF, of the middle ground. It takes into consideration, let's say, two different domains. And of course, for the example of IDF, you have the MCAD world and the ECAD world and vice versa. So because of that, it's trying to find a middle ground saying, well, what is the commonality that we have over here that we can pass along to each other? But the disadvantage of it, you see over here, is that it really reduces the domain to a common denominator. So a really good example of that, again, we're not talking about Desktop EDA right now. We're talking about strictly just IDF by itself. In the IDF format, a component is understood, which is a common denominator because you have a component both on the ECAD side and the MCAD side. But on the MCAD side, they probably have a nice drawing for it. Well, on the In the IDF format, it's represented as a block. Why? Because as far as it's concerned, it's not really worried about the primitives per se. It just wants to say, look, in this particular piece of real estate, there is some component over here, and I'm going to represent it by a rectangular block. And that's about it, right? Now, just not to go off too much on a tangent, I know that there is actually a new specification for IDF, it's 4.0, which is trying to address the 3D aspects of it. But you got to keep in mind that currently, and the one that's most commonly used, everything is represented by what they call a bounding rectangle. Then there's the intermediate format, and the intermediate format is where Desktop EDA really plays in, and also this new format called IDX. And by the way, I'm going to talk about IDX in just a moment just to give you a better idea of what it's about. But the advantages is that now you have a staging area, and that's really, really important because we're not really dealing with really just one format. We're not just dealing with IDF or IGES or any of the other formats out there. The biggest issue you really have is that the MCAD tool that you're using has its own native format to save things off, and the ECAD tool also has its native format that saves things off in. So what you do is you actually have an intermediate area where one part of the tool's purpose is to basically take whatever formats and idiosyncrasies of one tool, get it to the staging area, and then from there, the tool that's going to bring it into the other aspect or the other world is able to kind of pick it up, say, okay, I'm going to format this in a way that the other tool can read this in a lot easier. Okay, and that's what you're seeing with both the Desktop EDA and IDX. So I want to talk about these file formats. There's an amazing number of them out there. For every one I'm going to talk about today, there's probably about 5 to 10 of them that I just don't have time to talk about. The 3 that I'm going to talk about are the ones that you probably have heard of quite often and the ones that are used most oftenly, at least in the conversations I've had between those doing the printed circuit board designs and those people doing the mechanical aspects. The first one is the IDF, which is the intermediate data format. It was released in 1992. It was Mentor Graphics. Why did they do this? Because they saw right away, even back then, that they need to be able to exchange the data between these two worlds. So the IDF format itself understands concepts like silks and keep outs and copper and component, all right? And it had the ability to capture what I'll call the intelligent data. See, all the other formats really outside of this, for example, like IGES and even DXF DWG files, they're great because they capture the mechanical essence of it, but they never captured properties, okay? They were just drawings, and so you never got what they call the design intent behind those components that were being used. Then, of course, the limitations of it, as I mentioned earlier, there's really just using bounding rectangles, and the third dimension is nothing more than just the property value within the specification. All right, STEP. I think we've all heard of STEP at this point. Here's its acronym, Standard for Exchange of Product Model Data. And actually, the whole purpose behind STEP was to take IGES one step further. So IGES was primarily for 2D drawings. They realized by the early 1990s that they needed a 3D element of it. So they said, well, let's add a 3D element to it. And they quickly found that the IGES spec was just going to balloon very quickly because there's a lot of aspects of the 3D mechanical, right? There's positioning, there's surfaces, there's things that are specific to certain industries, for example. So when they created this, it actually became a bunch of not just one standard, but multiple standards. Now, I don't know if this is an exact number or not, but I counted 28 of them when I was doing my research. A good portion of them are very specific. One's built for mil-aero, another one's built for aircraft, another one's for, I should say built, they're written for aircraft, they're written for mil-aero, they're written for automotive, even one I think I saw for shipbuilding, for example. So they try to break this thing out into different industries. That's how big the spec has become. Of course, the advantage is really we're talking about the first time we really have a 3D data exchange here, and then is widely used and accepted now. So everybody has STEP, and as a matter of fact, if you're ever looking for a connector, you can go on to the manufacturer sites and you'll easily be able to find a STEP file for that connector over there. Of course, there's always the question whether or not they drew it correctly, but the fact of the matter is that you can go into a lot of these sites that are selling mechanical products and you can download the steps. So that's how popular and widely used it is. The limitations of this, I think we've all seen these things, especially if you ever worked in Altium. It's a single representation. So if you have to make a change to it, you've got to go back to the tool that you created it in, make the modification, then export out the step. So you can't just you can't really make modifications within the step itself. Secondly, the specification of step is really massive. As I mentioned, over 28 documents. So when you're dealing with the EDA tools, they're going to do whatever bare necessary in order to go from their tool out to a step file. Okay? The most common that you're going to see, by the way, as a side note, is AP203 or AP214, and I'm pretty sure there's a lot of differences between the two. However, the biggest difference between both of them is the color. Okay, so AP203 means that it's not going to have any color associated with it, as opposed to AP214, that if there was a color provided initially with that part, it's going to propagate along with the step file. And then, of course, inefficient file sizes. You got to keep in mind that this is a universal file in the sense that it was there for everybody to be able to pull in and use. And the way they did it was that everything, whether it was a single piece of silk or a trace, gets defined. And if you think about it, this is one of the reasons why Altium could not export either silk or copper in STEP, was just the sheer size of the files. We're talking gigabytes. Because let's take, for example, the number 5 or the letter S. That would actually take 5 strokes to define it. Okay? And so again, no matter how small or how big it is, it has to be thoroughly defined. And as a result, it just makes these things massive when you think of all the letters and all the lines and segments that make up those letters in the silk, or even the silks themselves, or even the copper themselves. So that's kind of the limitation of STEP. So this new format is called IDX. This is the one that Altium's been touting in its new 15 program, and you may have heard of it, but you probably haven't heard much about it, and for good reason. It's relatively new. It was released in 2010. There's an organization called ProStep that's promoting this here, and what they decided was that STEP is really cool because it's 3D. It's a great 3D representation, and IDF is really needed because, again, it was created specifically to go between the ECAD and MCAD world. Let's take the best of those things and put them together into a new format. Okay? And the biggest advantage that you're seeing over here, and this is why Altium was really touting this, is incremental changes, which we couldn't do in the older versions of Altium, because in particular, once you had your step file and you got it created and you pushed it over, that was it. And if you need to make a change to it, like any other step file, you had to go back to the native tool that was putting it together, make the modifications, and then export a new flavor of it. The biggest limitation right now is it's very new. It's not widely known nor adopted at this point. It'll be interesting to see if it is. One of the things I mentioned earlier is that there's just a number of different formats out there. It's just tens or dozens of them. And you just never know what the industry is going to do in terms of adoption. And the reason I say that is because it all depends on the dominant tool. It also depends on the dominant methodology at the time. So if all of us are following a certain methodology, then certain formats are going to lend themselves more so than others. Okay. The desktop offerings, these are what Desktop EDA offers. I'm going to kind of put them in two categories over here. First and foremost, there is a specific tool called Altium Modeler for SolidWorks. This is for those computers that have both Altium and SolidWorks on the same machine. So if you're kind of a smaller organization and you're wearing both hats, this is a very useful one because it basically uses the memory to talk with each other rather than having kind of an intermediate file that they have to kind of pass along to, that they use to read in and read out. So that's one way to do it. But if you are working in an organization where you have Altium or PADS in this case on one machine, and you've got your other type of MCAD tools on another machine, then you can mix and match it. You would purchase one of these, and you'd purchase one of these, and then they can talk to each other very easily at that point in time. I'll also make a note over here as well that if you're thinking about looking into Altium Designer, again, they did release their 15. They put out this new IDX product. There is one caveat to understand. The only tool that will read that in right now is SolidWorks, and it's the premium edition that will read that in. So if you don't have the premium edition of SolidWorks, it's not going to be able to handle the IDX capabilities that Altium is providing. So just want to throw that caveat out there as well. But for everything else, that's why Desktop EDA is here. So with that, I'm going to introduce to you Roger Castro. Roger is a 40-year-plus veteran of this industry. I've learned amazing things when I've talked to him about it. He's been using Desktop EDA when it was in its infancy back in like 2002, and he's kind of grown up with them. He's adopted Desktop EDA's products for his methodologies of going between the MCAD and the ECAD world. So with that, Roger, I'm going to turn the floor over to you here. So I'm going to make you the presenter. Roger, are you online?
Yes, I am.
All right, I can hear you loud and clear.
All right.
All right, and you are now the presenter, sir. And there's your face.
Oh, that's just what everybody wants to see. My name is Roger Castro. Good afternoon to everybody. I'm I've been using Desktop EDA for approximately 12 years or so. I found it to be very beneficial for me, particularly in producing documents that make sense. Here, what I'm demonstrating is that a little schematic that goes with this board. This board is not very large. It has a number of connectors on it and some other interesting little parts. Those items that are in this pinkish color are the 3Ds, and as you can see, we can readily convert that to 3D, and we can get some good detail out of this. The problem is how do I convey this type of information to the assembly house or to my customer? That this is your layout. Is this what you had envisioned for what this thing is going to look like? And of course, all the detail is here. This is coming in Altium, of course. You can see the traces and whatever. And if we zoom in, well, hold still. We can zoom in. We can even see the leads coming through the pads that are in the board. And we have the detail where these clearance holes are not even plated. So the detail is very good. We just can't readily convert this information to give to somebody, at least until I encountered Desktop EDA. Using their modeler, you can bring this up like this, and initially you can get a rough view of what it is we're going to be reproducing here in 3D in SolidWorks. And of course we have to go to a reference where basically we're going to tell it that where the board shape is located for this board, what the mounting hole prefixes are. We're going to use what is relatively called a fast placement. And when the parts are placed, we're going to reference them by their designator, or you can reference them by the footprint, or whatever you choose. And the orientation is classic in my case, i.e. this will be the front side of the board when the 3D is made. This is just document locations. I usually make the 3D go back to the original file where the PCB is sitting, and I point out where the parts models are. And then what methodology are we going to employ to select 3D parts? In this case, I use the footprint. I've found over the years if I name my footprint for the PCB and it has the same footprint for the 3D, it makes it very easy to match them up. I don't need any cross-reference file or anything else. Works very efficiently. Basically, on auto parts, i.e. these are for parts that will be made in case you don't have a 3D model already made. I usually use the bodies, and if I have step parts incorporated within those bodies, but don't have a SolidWorks model of that part, this will automatically create parts from the step model. You can't get much better than that or faster. In this case, on the outlining options, I usually pick a large board design and give it at least 20 iterations. That helps in the extrusion process. I don't need sketch text because I use stroke fonts. If you use TrueType, I would recommend you use sketch text. The merge copper features I usually leave off because it tends to extrude a little bit faster. For those who like doing their bombs in a 2D format, particularly if you're in SolidWorks, we can add a number of items to the definition of the parts. And if you make a 2D drawing of your 3D board, you can then bring in the bomb with all that information that we just selected. Very nice routine for those who like to do that. PDM, for those who use Vault in this type of operation, this will probably work very well. And for the EPDM, it's not quite operational at this time. Meanwhile, when we get to the board, you can come in here and set up what it is you want specifically on your board. We're going to be doing the board outline, which we defined as being on the board one layer, mechanical one layer. Pinholes, these are anything that's not a via. Then we're going to do mounting holes, via holes, and we can come down to here. You have a choice between top layer and top and bottom or multi-layer. I usually just stay with the top and bottom because I'm just interested in showing the assembly items from this. This would come in handy if I were doing some thermal analysis. But meanwhile, this is a double-sided board, so I want the pads, the vias, the traces. There are no polygons on here. Silkscreen and silkscreen text. Now, there's a couple of routines you can run to ensure that there are no mismatches on your PCB. And one of them being the traces, where we can run and check for gap errors. Now, this routine checks your board over to see if you have gap errors, because it's pretty peculiar on how they go together. You just can't have sloppy traces. This thing looks like it has passed without too much trouble, and so we're clear to go. And one other thing we have is the component. And here, you can selectively turn off and on which ones you want to show. So if you don't happen to have this particular model here, and you don't want to make any effort to see anything, you can just turn this off, and you don't have to worry about it. But other than that, it's pretty straightforward. You can do this setup in just a few seconds. If we were going to make a 3D at this point in time, we would click this button right here. If I have the components checked, it will make an assembly. If I leave components unchecked, it will make a board. Now, we're going to pretend that we've done this routine. We're not showing it here because of the time element involved. But basically, here is the board as it appears after it's been made. As you can see, it brought in the parts, it put the traces in here, it's put the silkscreen in here, it's put the holes in here. And again, Desktop EDA does such a good job of extruding this. These holes in this particular are not plated. It shows them as such. Whereas if we were to look at a via, we would find that that hole is plated. So I mean, you get authentication all the way down to whether it's plated or not plated. These traces are approximately 1.5 mils, 1.4 mils tall or thick, because I asked it to do 1 ounce copper. And so here's a good overall presentation of this board. Now these parts I made myself in SolidWorks. You can download them from say 3D Content Central or Parts Online, any of those other places. Just be mindful that they're not all in the correct orientation to fit your footprint, nor are they necessarily in the right plane. If we look at this, we can see if I have to the front plane, that's what's shown. That's the top view of the board. If you bring in parts that are done, that are referenced to another plane, they're not going to line up quite this easy. Now, some people have said I can make a step file from the PCB, which is true. We can come over here, save as, step or whatever, and there it is. You click that and it'll make a step file. And I can import this same step file into SolidWorks. And here's an example of that. As you can see, it's exactly the same as the 3D that I made in Desktop EDA, except there is no traces, there's no silk screen, there's no reference designators, and there's no pads. The only thing that's in this board are holes and components. And these components are, of course, the ones that I've made. If you don't have them, what you're going to get is little gray cubes that will represent these parts. You won't be able to tell if they're male or female, through hole or surface mount. You might be able to tell if they're through hole because there's obviously holes in the board, but at first glance, it's just going to be a gray cube. You don't have any information on that. Now, this step file coming out of Altium is 16 megabytes in size, whereas the board that's made using Desktop EDA is only about 4 meg in size. If I save that board as a step file, it increases to about 46 megabytes in size. So without the silk screen, tracing, and plating, it's only 16 meg. With all those additional items, it's 46 meg. Now the problem is, I have a 46 meg file, in this case the one we're looking at, and I want to send that to somebody, be it a customer or whomever. It's 46 meg. Well, that's not going over the internet through your email, none too easily. So you have to get a Dropbox or something equivalent to convey that information to the recipient. If they happen to have a step file reader, that's fine. If not, they'll have to download one off the internet. Of course, if you're sending this to a mechanical person, their mechanical work is more or less finished. I mean, all these parts are made to size. The whole pattern is where I want them on the board. They can put this into a package or some enclosure and be rest assured that what they have is what it is. Now, we can save this file in SolidWorks by simply just coming over and saying, I want to save this as a PDF. Right there. Some people don't know that if you click this item right here, save as a 3D PDF, you can in fact put that in a 3D environment in a PDF file, like I've done here. And here is this board in a PDF format. You can send this PDF format to anybody who has PDF, almost PDF 7. And they can read and manipulate this file as they see fit. Here's a backside view to this. Here's the front side view. You can zoom in as close as you want. The detail is immaculate. Now this is the type of 3D assembly that I can get from Desktop EDA that I include with my assembly documentation for the assembly house. And I have never had a problem with the assembly house when I send them a document similar to this. I usually tell them if you have something and it doesn't fit, there's an error right away because this document is correct. So you might have received the wrong part by error. You can alter these. You can go to a shaded illustration if you like. There's a number of things you can do in this format that you normally can't do anywhere else. So we have where we can make a 3D PCB. We can save it in any number of formats that we wish, be it PDF, be it STEP, be it IGES, to send off to the mechanical people. And then we can make assembly prints. Excuse me. This is not an assembly print, but this is an item where you can even do multiple stack-ups. There are 5 boards in this stack-up. We have one here, one here, one here, the antenna board, and we have these 2 boards, and this little board over here. We have 6. Every one of these were done with Desktop EDA and then assembled to make sure that all this would fit together inside of a case. I don't know how else I can present documentation with such detail without using this technique. And of course, you can zoom in here as close as you want. And all these parts that are in here, I made. And then I color-coded a lot of them. These are capacitors, these are resistors. And of course, you can tell the ICs. This little purple thing over here is an inductor. This guy right here. So the documentation effort is greatly enhanced by using this type of technique. And of course, you can hide things as you see fit or make them visible, not visible. Underneath that shield cover is a number of components. Here's a BGA and some 402 capacitors. So the opportunities to use this are endless. When you get to the paper prints, this is a little one-sided board where basically I inserted the 3D out of Altium into the board. This is a silk screen, but I made a 3D model of the board, and with that, I place that inside of a 2D PDF. So I can actually come in here, and here's a 3D assembly of the board inside of a 2D PDF. This is part of my documentation. So if somebody has an issue with how something is going together, for example, this connector here, I'm sure that most of you recognize that this connector is actually mounted incorrectly. It turns out this was a special technique for mounting it to a connector, to the mating connector. So we have a number of opportunities here by using Desktop EDA. I really can't think of another way of doing it better. And so with that, I've about concluded what my presentation was. And I'm going to sign this over to Paul. So Paul, it's over to you.
Roger. Thank you, sir. If you don't mind, I'm going to leave your screen up over here because I'm going to introduce Brian. Brian, if you can take yourself off mute over here, let's just do a quick sound check. While he's doing that, we also got some questions for him.
Can you hear me?
There we go. Now I can hear you just fine. So, Brian, actually, let me just tell everybody in the audience there, feel free to write the questions in. Unfortunately, we can't open all the lines up. It makes it really difficult since we have quite a few people here today. Feel free to write the question in, and I'll be monitoring that, and then I can just ask Brian directly. Brian, I want to start off with this question. It's going to be kind of an interesting one. We actually have a number of people in the audience who are interfacing with individuals that have ProE. And they were just wondering if, A, you've got a tool coming out that's going to address that, or do you have any recommendations that they they may have to try to interface between EDA and ProCAD. Any EDA tool ProCAD.
Okay, well, ProE have supported IDF from the very beginning. It's built into the product, so we've never taken the approach of trying to compete with that. But my recommendation for interfacing to ProE is use our IDF tool in Altium and output the IDF, which can then be read in by ProE. We've got lots of ProE customers, and it works very nicely. With traces, because the way we do traces with IDF, it is a standard IDF section that we hold the traces in, so ProE people can read them in. It's not quite as transparent as if you've got our IDF at both ends, but you can do it with ProE.
Okay, so in terms of getting them set up, they would purchase the, let's say for instance it was an Altium, they would purchase the IDF modeler for Altium Designer, and then from there it would actually be able to, ProE would be able to read out the subsequent file from there?
That's correct.
Okay. I'll have to add that to our list of
MCAD. And there's full bidirectionality. ProE supports export to IDF as well, so it does handle the bidirectional stuff very well.
Okay. There was another question here. Does it automatically pick up the solder mask color assignment in Altium?
Not yet. That's probably the next feature we'll add, but at the moment we don't support solder mask. What we do is you can color the way we set the copper up. You can quite easily color the pads and vias in a different color to the traces. So you can quite easily do that. Get at least the view that you've got a solder mask, but at this point we don't actually do the solder mask, but it's coming.
Okay, very good. And just looking at a couple of the other questions over here. One question that came up, if you have a number of copper layers, can you choose the copper layers, which copper layers come into SolidWorks? Because this is very important for thermal modeling.
Well, you saw that when Roger was setting it up, you've got an option of either going top and bottom mode or multi-layer mode. And when you go into multi-layer mode, you can expand it out into layers. But and selectively not do, say, polygons, but I think in practice you either do top and bottom layer or all layers and do the traces for all layers.
Okay. Another question. We got a lot of great questions coming in over here. Can it pick up things like plating, such as ENIG?
Sorry, can you repeat that?
Yeah, so one of the questions was, and I think it was kind of a continuation of the last comments, can it pick up plating such as ENIG?
I'm not familiar with ENIG, but anything you describe in Altium, you'll get in SolidWorks, like blind and buried vias. The plating for that gets sorted out, but ENIG, can you tell me what that is?
Oh, it's let's see if I remember. It's a electroless nickel. It's in gold, I think, and I apologize if I'm butchering this over here. It's basically a coating that you'd put over your copper to prevent certain erosions. I'm very vague about it. But you may want to actually show that. But that's what I was being asked.
Yeah, we don't provide a specific feature for that.
Yeah, I got you. So as long as you have a mechanical layer that represents that, or I guess in theory you would have to, and not to get too technical with it, but in Altium, if you turn one of your copper layers into something that would represent that, I suppose that it could be represented as that
Yep.
from a mechanical point of view. Okay. Just a very quick question, Wayne. I think I can answer this one pretty quick for you. You asked for support for SolidEdge. There is an IDF tool for SolidEdge. Is that correct, Brian? Yep.
Yep. And that will allow you to do traces and silkscreen as well.